All right, what's up, everybody? So today we're going to finish out our discussion on light. Okay, so we've talked about what light is, how it's created, what's color, all these sort of things, and so we want to take just a moment here to look at these last two vocabulary terms. Okay, we've got these two terms that are known as reflections and refractions. Okay, so first of all, we're going to start off with this idea of the refraction of light. Refraction of light is simply the bending of light as it moves from one material into another. Okay? And if we can get that light to bend enough, we can start talking about it in terms of reflection of light, where light will come in, it will hit a different material, and it will rebound back into the material which it came. Okay? So like I said, we're going to start off with the idea of the refraction of light, talk about this bending of light, why it happens, how can we utilize that, and then we'll shift our focus over to the reflection. So we'll talk a little bit about this idea of lenses and how those will be useful and how we can utilize the shape and material of lenses to help us see better. And then we'll move over into mirrors and how different shapes of mirrors can allow us to see different interesting things. Okay? So let's first start us off with this idea of the bending of light. Okay? So if I start off and I've got some sort of material, let's say it's glass, and I've got light, and that light is transmitting through the air, okay? So say it's going to be coming through the air, and it hits that material. Well, when we go from one material where light has a certain speed in it to another material that light will travel at a different speed, right? We talked about this before. If we've got light that's going through a vacuum, it's going to be going about 300 million meters per second, very, very quickly. And as we start going into things like water or glass, it's going to slow the rate at which that light ray passes through it. Okay? And so the more we have a change in the speed of that light ray, the more we're going to have a bending of that light ray. Okay? So if I've got a light ray and it's coming through the air and it's going to hit this glass, right? Glass is much, much more dense than air. And so it is going to bend that light ray significantly. And then once it exits out of the glass and back into air on the other side, it's going to re-bend the same angle that it was when it entered. Okay? So again, the big thing that this looks at is that the more it changes the speed of the light ray, the more it's going to bend the light. Okay? So that's the big thing to take out of this. Now, what are practical applications of this? Why do we care about this? Well, first of all, there's the apparent, like, hey, if you wear glasses, this is the technology that we're going to utilize for this. But for those that don't wear glasses, you have definitely experienced this at some point. I want you to think back to a time where you're at some body of water, maybe it'd be a lake, maybe it'd be a pool, and you look down into the water, and there was something at the bottom of the water, and you're like, I want to grab that. Well, if I go ahead and take my hand, and I reach down into the water, and I go to grab something where I see it, I might just miss it. Okay, well, why is that? Okay. Well, if I've got some amount of water, okay, water's right there, and there is something down there, let's call it a fish, okay? A little smiley face, make them happy, okay? And as I look at that fish, okay, my eyes are going to come down, and I'm going to think that the fish is right there, okay? That is where where I see the fish, okay? I'm assuming that it's right there. However, that fish is not actually where I see it. Because as that light comes down, we go from the air to the water, and it might bend that light, and so the fish might actually be down there. Okay? So if you've ever reached into a body of water for something and you're like, hey, I want to grab that, and it's not where you thought it was, it's because not that you saw it incorrectly, but the water itself changed how you perceived the things that were down under the water. Okay? So, like I said, a lot of us, we might need some glasses to fix our eyesight. So what are some differences that we can utilize this idea and this technology for us to see better? Okay? Well, there's two different really styles of lens that you might see. Okay, so I'm going to erase this. There are two different types of lenses that we're going to talk about today. There are what we refer to as convex and concave. Okay? So in a concave wave, the lens is going to look something like this. Okay? It's going to be thinner in the middle, thicker on the outsides. Okay? And a concave lens, what you're going to do is the light's going to come in, and it's actually going to diverge that light outward. Okay? It's going to diverge that light outward. If we have a convex lens, okay, that's going to be the opposite, where it's thicker in the middle, thinner on the outside, and that is going to be a light source comes in, it's going to hit it, and where this was divergent and it spread that out, okay, this is going to narrow, okay, and it's going to focus that light inward, okay. And so for some people that might be far-sighted, some people might be nearsighted, it depends on where the light as it enters into your eye, where it focuses, right? Because different people might have, as light comes in this way, light comes in and it goes this way, light comes in and it goes this way. If the light is converging, your focal point is in the middle of the eye, and by the time it gets back to the retina where you actually see, if it's out of focus back here, we want to figure out, can we get some sort of lens that maybe diverts the light a little bit so that as it enters the eye, it refocuses into the back of the eye. So let's look at this. If the focal point of the eye is in the middle of the eye and not the back of the eye where we want it, we may want to use a concave lens, diverge that light out a little bit so that as it diverts outward, as it comes through the eye and it converges it back again, it moves that focal point back a little bit. If we, on the other hand, have the problem where the focal point is back here, we might want to use a convex lens and converge that light a little bit sooner, giving that focal point back to the back of the eye into the retina where we actually see things. Okay? So these are two different places where we can visually utilize this in our everyday lives. Okay? Now, we can take this idea of refraction, and I said that depending on the angle and the change in the speed is going to determine what angle it's going to be as it goes through the material. Now, it's really, really interesting that we can actually take that kind of to an extreme. So if I take a little bit of light, okay, and I have got something that's shining light upward, okay, it's going to bend the light a certain amount, right? Okay. Now, if I keep changing this over more and more, so maybe I'm going this way, it's going to bend it more, and we can actually get to a point where we come in at such an angle that it redirects and it bends it so much that we have internal refraction, where it refracts the light, it bends the light so much that it actually reflects back into the material where we're going, okay? So we do have a situation where this could occur, and we actually utilize this quite a bit in telecommunications. If any of you ever heard of the idea of optic fiber, okay, or fiber optics, sorry. If you ever have optic fibers, this is just, hey, we're going to take these strands and we're going to make these of glass or plastic or some material, and we can shine light through them. This is actually going to vastly increase the rate at which we're sending a lot of this telecommunication information. Okay? If we've got things that are made of metal, right? Metal is something that it's going to be, maybe a little bit harder for the electricity to travel through, right? There's going to be a little bit of resistance to that material. But if we have these little tubes and they're filled with nothing, if they're in a vacuum, well, light in a vacuum is the fastest thing that can possibly move, and so the information that can send through that would be vastly superior to regular metal cabling. Now, one of the problems is the reliability, not to say the durability of those are definitely less than a traditional metal cable. But you're kind of giving up, do I want this to be a little more durable? Do I want this to be a little bit faster? Do I want it to be cheaper, more expensive? What is your budget? Things like that. So there's give and takes on how we can utilize this stuff. But yeah, we can utilize this idea of internal reflection because of the refraction of the light so much. We can utilize this in all sorts of really interesting technologies. Okay, let's shift our focus now to the idea of reflection. Okay, when we talk about the reflection of something, all we're talking about is, as you think about, like, oh, if I go and I look at a mirror, I see my reflection in the mirror. Okay? Now, all that means is that as light comes in and it's going to hit a mirror, that light hits it and bounces back off. Okay? Now, there's a law that we need to understand in order to truly understand the idea of reflections. Okay? And it's called the law of reflection. And what that tells us is that if I've got some reflective surface, okay, and I've got light that is coming in to hit that, whatever this angle is, okay, so whatever the angle between the light ray hitting the reflective surface and the reflective surface is going to be the same angle at which it reflects off of, okay? And so when you think about, when you're trying to figure out what you're seeing, where you're going to see it, where the light's going, just realize that if you come in and you shine the light at a more, or a less steep angle, it's going to reflect off at the exact same angle, right? So if I have a light ray and it comes straight down, it's going to come straight back up, okay? So that's the law of reflection. So whatever angle is going to come down and hit the surface is going to bounce off at the exact same angle. Now, kind of an interesting side note on this. Why is this true? Well, scientists had this thought, and they're like, it shouldn't really matter what direction it bounces off of because the light comes in, it hits the material, it's going to absorb that energy, and it's going to re-emit that energy in some direction, and it could be in any direction that it re-emits it. So why is it that it's always, it comes down, it hits, and it reflects off at the exact same angle? Well, there are some very, very smart people that use some very, very complex math. They used a lot of calculus in this, and what they did is they're like, okay, if I have this ray coming down and hitting this material, and it gets absorbed, and they did some calculus where they said, well, what if the energy that comes down and hits this material, it's now going to emit that same amount of energy in every direction, right? Because there's an equal possibility of when it comes down, it hits and it bounced that way, another one that it bounced back this way, and directly that way. And they did the calculus, and they're like, well, what if we looked at the constructive and destructive interference that would occur if every one of these waves occurred all at the same time, right? Including this one ray that's coming in this way. And they found that if you took all of these rays in all these different directions and you had the one ray that's coming in this way, the resulting ray that would be left after all of our destructive and constructive interference between all these different rays would be that one. That would be it. That would be mathematically what was left if all of these things occurred. So if we were taking these ideas of calculus, right? If any of you guys decide to take calculus, or have to at some point, there's some really, really interesting concepts and ideas that we can pull out of this. Okay. So just like we talked about before, where we had these ideas of concave and convex lenses, we can actually do the same thing with a mirror. Okay? So if we erase this, and I've got one mirror that's like this, and another mirror that's like that, right? We said this was a concave lens. Well, we're now going to look at this as a concave mirror, and we had this as a convex lens. We're going to look at this as if it is a mirror. Okay. Interesting way, if you're having a hard time remembering these, a trick that I use to remember this is the concave mirror. It bends inward, just like a cave you go into. So this is a concave mirror, or concave lens, and this would be the other one, convex. Sorry, I give you the example to help you with this one, and then you just remember the other one is, well, the other one. Okay. So with this, as we have light that's coming in, because we said that the light bounces off at the same way that it hits, it's going to come in and bounce outward. Now, because it bounces outward and it expands over a greater area, it actually makes the thing that you're seeing in the mirror a little bit smaller. Okay. Now, the advantage of this is you can see more things because they're smaller. Okay? Or we've got this one where it comes in and converges together, okay, making things look bigger. So depending if we're looking to have a concave or a convex or a concave mirror, will determine whether we're seeing things as being bigger or smaller in them. So if you ever go to, I don't know, say the fair, and you see the fun, or the what are they called? The mirrors that in the fun house, and they make you look all weird. It's because they have concave and convex mirrors in there that are displacing how the light is coming off of it and making you look kind of funny. We can look at things like this where maybe you're trying to, look in your side mirror in your car. Well, if you look in the side mirror of your car, you're going to have a couple of convex lenses so that you can see a greater amount of stuff, right? And this is why it says, like, hey, objects are bigger than they appear, right? Because this is going to make them seem smaller so that you can see more stuff, right? So, all right, that's everything I needed to get through today. Again, hopefully this idea of concave and convex lenses helps. And that is the end of this unit. So I'll see you guys later.